Hi, I'm Francesc Campoy, and today I'm going to be talking about something weird that people do a lot, but not in Go. So I'm going to try to do it in Go and show you why it doesn't work. So I've been here before. This was 4 years ago, 2014, off by one. 2014, I talked about what things I learned by teaching Go. Then I talked about how to do functional programming in Go and why not to do it. And following the same logic, I'm going to do today how to do machine learning and why not to do it. So, but actually, it's better than it sounds, so wait for it. So machine learning has a really interesting history, and there's amazing points in history, such as the bombing in 1996, when Deep Blue played against Kasparov. This was amazing. It was super exciting times for computer scientists. Everybody thought that machine learning was the great thing that was about to get there. We're going to have things that understand us completely. Like, nowadays, you can talk to your phone. They thought that that would happen like the year right after, right? So it was really, really exciting times for computer scientists, not so much for chess players. Look at that face. He's really not happy. But that was a really great moment. And even though everybody was super optimistic, they were talking about Go, not the programming language, but the game. And they were saying that it would take at least 100 more years before we can play at a human level, a professional human level, let's say. Because I'm sure any machine can play better than me. I have no idea about how to play Go. 20 years later, though, AlphaGo, which it's very famous, created by DeepMind, played against Lee Sedol. And Lee Sedol is the best, well, is the best human player of Go in the world. And this was incredible. It was on TV, everybody was watching it. It was really, really cool. And AlphaGo won. And Lee Sedol was super happy about it. I guess it's a different community. Chess players and Go players are quite different. The cool thing about this is that this is just the beginning, right? Like, we got, so AlphaGo Fan, which is the one that played against Fan Hui, was one of the first versions of AlphaGo. And it was pretty good, and it won 5-0 against Fan Hui. Fan Hui is a professional player. Then we got AlphaGo Lee, that played against Lee Sedol and won 4-1, which is really good. Then we have AlphaGo Master that was created afterwards, and he played online only against 60 professional players, and he won every single one of those games. And recently, AlphaGo Zero was announced, and it beats AlphaGo Lee 100-0, which is mind-blowing. And it beats AlphaGo Master, the previous version, 89-11. Now, the crazy thing about this is that in order to build these neural networks, what we're doing is we're training them with a lot of hardware. So with Fan Hui, it was 176 GPUs, which is a lot. And all of these GPUs were distributed. Then we moved from GPUs to TPUs. GPU is graphics processing unit. TPU is tensor processing unit. It's specifically designed for TensorFlow. So only 48, still distributed. Master and Zero only use 4 TPUs in one single machine. And this is the part that is amazing, right? Like, we're moving forward. It's not really the hardware. We're creating new techniques that are amazing and able to do crazy things that we thought were not possible. So in 40 days, without playing against any player, any human player, AlphaGo Zero is able to reach levels that no one else had ever reached before. So machine learning is a thing, and it's cool. Machine learning, what is it by itself? Like, what is the concept of machine learning? Because there's a lot of concepts of machine learning and artificial intelligence. It's good to have a good definition. The definition by Tom Mitchell is, a computer program is set to learn from experience E with respect to some task T and some performance measure P, if the performance on T's as measured by P improves with experience E. 3 pieces important are here. Experience E and task T. We do something specific, right? Like playing Go. And we learn over time, the experience. We need to play over and over, like 40 days, for instance, to learn the thing. Now, there's also a really important part, which is performance measure. We need to be able to tell how well or bad we're doing in order to improve. And this is something that is valid for machine learning, but basically for anything you're doing in life. You don't know how well you're doing, you cannot know if you're improving or not. So it's important to also define that. So let's go with a simple. I could have done AlphaGo in Go, which is amazing, it's super cool, but that's too hard. So instead, we're going to do MNIST. MNIST is this data set that is super famous. It's basically every single person that has done something with machine learning has done this. It's like the hello world of machine learning. So what we're going to do is we're going to learn how to tell what character is every single one of those images. The task will be recognizing the characters. The performance measure is how many of them are correctly labeled, because we're getting also labels. And the experience is we're going to do prediction, see how good it is, and then try to improve it. And we're going to go over and over on this. So what's the input? The input is an image and its label. The image is 28 by 28 pixels, and it's not only one image, but many of them. There's actually 60,000 images in the data set. So what we're going to do is we're going to be using logistic regression. And I'm going to go really fast over this, and there's a Coursera course that is amazing on this, machine learning. Check it out, really good. You'll have the time to learn this. But basically, the important part is we're going to be predicting with this. We have the input, which is the images. We have some weights and some biases that we can play with, that what allows us to try to learn. Learning, in this concept, is modifying those matrices. And then we do a prediction. Then we compare it, and we decide if this is good or not. The cost function is how well we're doing. It's that performance measure. And it's just an average of how well we're doing in general. That distance there, the dist function, it could change depending on what problem you're solving. In logistic regression, we use logarithms, but for other things, we use something simpler. And finally, we optimize this. Easy, right? How do you do it? Well, you have a function, you can do a derivative of that function, then you have everything you need. And there's algorithms for this. And the only thing is that these algorithms depend on a lot of matrix multiplications everywhere. There's matrices everywhere, literally. So how do you do this? Well, it's easy. You install TensorFlow, or Keras, or Theano, which all of these are written in Python, or Apache Spark, or Deep Learning 4J, which are in Java, or this one here is Octave, which is an open source version of MATLAB. Or you go like, let's do it in Go. This is a Go conference. What could go wrong? So what do we need for Go? We need to be able to read images, so reading files. Go is really good at that. We need to be able to multiply matrices. Let's see how good Go is at that. Visualizing data sets. And finally, we need to be fast, because we have 60,000 images. We need to go really, really fast in order to achieve something that is useful. So as I was saying, GoNum is the one that everybody knows, right? GoNum is really cool. It's super powerful. It allows you to do many, many things. It's like the equivalent of NumPy. If you ever use that in Python, you have GoNum in Go. I keep on calling NumGo, because it's NumPy, but it's called GoNum. And it provides many, many different things. One of them is matrix multiplication and algebra in general. Also comes with statistics and probability, and it allows you to do integration and derivation of functions and optimization and all of these things. And there's way more than that. Also comes with plotting, which is really powerful. It's like PyPlot. If you've used that, the equivalent is GoNumPlot in Go. Cool. So let's use it. I told you that there was this cost function. This is a cost function not for logistic regression, but for linear regression. Slightly different problem. But what does this look to write in GoNum, or in Go with GoNum, to write this? And it looks something like, so it's matrix multiplication minus some other vector. We do everything squared, we sum it, and divide it by something. It looks like something like this. And it's not bad. But there's many lines. There's every single operation is one single line. And there's a thing that I really don't like, which is that matrix X, H, keeps on changing over time, right? Which makes sense, because you want to reuse the memory. So what you're trying to do is mutate the matrix over time. But 2 years ago, I gave a talk about how mutability is not something that really, really helps you all the time. So I really wanted this to be immutable. So I was not very happy, so I decided to fix it. So I implemented the wheel, and I open sourced it. So this is a package that I do not recommend anyone to use yet. Rather than focusing on the performance of the package, I focused on having a nice API that is easy to use and hard to misuse. And having immutable matrices is a big part of it. Finally, it only supports float64 because that's the one I care about. If you care about something else, fork it, send a PR, we're friends. Cool, so what does it look, the same function written with this package? Slightly simpler. You have a product of two matrices minus y, and then you do the dot product, you sum it, and divide it by something. In my opinion, this is much easier. It's especially harder to make it wrong. Like, if you're missing something, there may be some errors in there, but they will be quite clear. When I was using numgo, GoNum, I told you, when I was using GoNum, it was quite normal for me to just forget what piece of the formula I was translating. Cool, so with 60 minutes of time, let's do a demo. So the first thing is, if you do machine learning, the first thing you want to do is you want to plot all of the things, right? And in Go, plotting things is hard. But you can also plot images into the output. This is item 2, and I created a package called ImageCat, and it allows you to do these things, which is really cool. So it allows you to see the input. There's a 4, that's a 4, a 1, that's a 1, 3, a 3, etc. When I press Enter, we're going to start training that. We're going to go over all of our images and try to increase that accuracy. When the accuracy reaches 100, or we reach 30 seconds, the program will finish. Hopefully, the accuracy will, OK. So now we're able to predict all of the images 100%. Yay, OK. So now, with actually using the 60,000 images, not 100, so if you remove that line, how do you comment things? There you go, and you save, and you run it again, and this is what you get. So this iteration 1. I'm going to wait until iteration 2 and then stop it, OK? Because I think it's around 25 seconds. OK, there you go. Oh, that was faster. That was actually really good. OK, so yeah, not really good. It's kind of painful. And after 30 seconds, the timer will appear, and we'll reach something really bad, something around 50%. And random is better than that. So not amazing. OK, so what's going on? Well, matrix multiplication, if you do it using only one Go routine over just one CPU, is not the best thing you can do. So what I did was I wrote, where's this? Fit. OK, so this is the function that we're using. And when we're multiplying, we're using mat product. And this is set to be just the product, which is the linear product. I also created a parallel product. The parallel product is simply using one Go routine per row. So that way, we're creating 60,000 Go routines and letting the Go runtime just do that. So let's see if that works better. Did I change it? Yeah. So that was fast, but that was not it. OK, so this is faster already. We got 20 seconds before. Let's see how much the actual first iteration takes. And I hope, OK, 10 seconds. Cool. This is still really bad. This is incredibly bad. If you do this with Python, it works much faster. And why is this? Well, because Python doesn't do Python. It does C. So what I did was I went back to GoNum. What I did was this function here. It adapts my matrix into a GoNum matrix. They're really similar, so it's quite easy. And then I call the gem functions, general matrix multiplication. And by doing this, but just by changing that line there, when I run it, now we're getting into something that is almost acceptable. This is still not as good as we wanted, but actually, let's let's wait for 30 seconds and see how good it gets, and let's see what the mistakes, where it was not able to reach what it wanted. Let's see. In the meanwhile, these are all of the references that, all of the things that I wrote for this talk, so if you want to check it out. The slides are also online already, so they're on speaker deck under my username, Campoy. That is not what I wanted. OK, so let's see. These are the things that we didn't get right. And there's many of them, so I'm going to stop it there. But please, die. OK. Yeah, image cat, it doesn't. OK, so let's stop it there. OK, so this one, no, it keeps on going. OK, that doesn't work. But you can see that some of the numbers, like there was a 4 that almost looked like a 9, and predicted it was a 9 instead of a 4. There's mistakes that kind of make sense. Like, well, that 5 to 7 doesn't really make sense. But this 7 to 1, well, kind of makes sense. So if we were training this for longer, we would achieve something around 98% accuracy, which is actually pretty decent. It's not the record by far, but it's something that we can start doing things with. So at the beginning, it said that GoNum was not of my taste, and I still maintain that I think that their math package could have a nicer API, so that's what I'm working on. I'm trying to provide a nicer API to the same GoNum backend using BLAS, which is the linear algebra thing written in C that we're using. But there's more than that. I'm not using GPUs, and there's a lot of possibilities of using GPUs with OpenCL or CUDA. What about if we created a port of TensorFlow, and TensorFlow was available from Go? That's crazy. But what if you instead had a binding so you can write your programs in Go using TensorFlow? Is that even possible? Maybe. I don't know. And I hope you will help me. Thank you.